Morning. This is section 15.3, Hess's Law in your textbook. So Hess's Law is fairly straightforward. It simply means that if you have a chemical process, it's only the enthalpy change over the entire process is dependent only on the initial and final stages of the process. So that means if you have, for example, a multi-step chemical change or physical change, you can actually determine the overall enthalpy change by adding up the enthalpy changes of each of the steps. And in some cases, this is quite helpful because it allows us to do things, figure out enthalpy changes based on those multi-steps rather than going through the entire process, which may be more difficult in terms of determining the overall enthalpy change. The way we write it out mathematically then is the overall enthalpy change, delta H net, is equal to delta H1 plus delta H2 plus delta H3 and so on, however many steps there happen to be. The other way, writing down using the sigma notation for the sum of all the enthalpy steps. One of the things we have to also realize is that if the equation is reversed, so if you run the equation backwards, then the sign of the enthalpy change is also going to be reversed. Okay, so it'll be, if normally it's an endothermic reaction, then your delta H will be positive, and reversing it makes it an exothermic reaction, so then the delta H has to be negative. If the coefficients of the chemical equation are altered by some multiple, then the delta H value has to be altered in the same way, right? Because remember, your delta HR is a molar enthalpy. So let's do an example here. Formation of carbon monoxide. We can't study it calorimetrically, so we can use Hess's law then, using the heats of formation for carbon monoxide and carbon dioxide. So the heat of formation of carbon monoxide, that's what we're looking for. Let's use instead the combustion reactions for carbon monoxide and carbon dioxide. So first of all, for carbon dioxide, we know the heat of combustion is negative 393 kilojoules per mole. For the oxidation of carbon monoxide to carbon dioxide, we get heat of combustion of negative 566.0 kilojoules per mole. So let's take these two reactions then and their enthalpy changes and figure out what the heat of formation or the enthalpy of formation of carbon monoxide is. So what we do is we rearrange those equations so that we build the desired reaction equation. So first of all, we have carbon and oxygen on the reactant side. Let me just back it up. All right, so we've got carbon and oxygen on the reactant side, carbon monoxide on the product side. So we want to rearrange these so we have that situation. So the formation of carbon dioxide, we can simply use that reaction the way it is because it gives us carbon and oxygen on the reactant side. We have CO2 on the product side, but we're not going to worry about that just now. The second equation, if we take that and reverse it, that gives us carbon dioxide on the reactant side, which will then cancel with the carbon dioxide on the product side in the previous one. And it will give us carbon monoxide on the product side, which is what we want. This half oxygen here will probably cancel with some of this oxygen here, and will probably be set. So let's add these two together and see what we get. All right, carbon dioxides cancel. We're left with a carbon. We're left with this one oxygen cancels with half of this oxygen, leaving a half oxygen. And then we have carbon dioxide on the product side, carbon monoxide on the product side, which then is our desired product. All right, so what we've done is we've taken the heat of combustion of the first reaction. We've written it down just the way it is. That number stays the way it is. This one, though, we reversed, which means we have to change the sign here. We also, if you'll notice, compared to the original, we divided by 2. So rather than the 566, we've now got positive 283 kilojoules. We add this up, we get negative 110.5 kilojoules. And so that's the formation for carbon monoxide. So just to summarize, basically what we're going to do is just take these reactions and try to build our desired reaction based on the reactions that are given, and then simply use the enthalpy changes for those reactions, add them up in the necessary way to get the overall enthalpy change. So the steps: write the net reaction of the equation that isn't given, if it's not given. Manipulate the given equations to yield the net equation. Cancel and add the remaining reactants and products. Add the component enthalpy changes to obtain the net enthalpy change. And you're done. All right, so there's the homework questions. Give those a try. Again, if you have questions, post them on the discussion page, and I'll put in some answers for you if you need the solutions.